right, 6.6 is our application section. A really common application that I'm sure most of you guys have talked about in chemistry is radioactive decay. So we use carbon-14 to date different fossils because carbon-14 is found in, I think, every living thing, I believe is what I learned a long time ago when I took chemistry. And carbon-14 has a really long, what we call half-life. And so a half-life is how long it takes for this atom to decay to half its original amount. So it says carbon-14's half-life is about 5,700 years. And so I'm going to walk you through the process of how they solve for that. So we're going to use our equation. This is the same thing as the equation that we used for continuous compounding. We had PERT, where P was that principal. Well, A is still that initial amount. E is that base that it's multiplying in. This only says negative K because it's decaying. That's the same thing as the R right here, the rate. It's going to come out negative regardless, so you don't have to worry about knowing that it's negative K for decay. And then the T is time. These are the exact same equation. They just change the variables on you to fit this chemistry situation. So if I think about it, if I want to know when it takes for something to decay to half the amount that was present, so I'm going to think about half the amount. So I'm going to say 0.5 for half is equal to like 100%, 1, the original amount, E, whatever K is, we don't know, but I do know that it is 5,700. So what I'm going to do is I'm going to use this concept of half-life, and I'm going to solve for that decay rate. All right, so the 1 in front here doesn't really matter. So I'm going to do natural log on both sides to clear out that E. So when I do that, I have ln, and I'm going to go ahead and switch this to 1/2. Equals, that E is ln and E, they're gone, K times 5,700. So we're divide that off. It looks like I have K equals ln of 1/2 divided by 5,700. We're going to put that in the calculator and look at what it is. It should be negative. Notice we had negative K right there. We'll see what it is. When we use this equation, though, we are going to use the actual value for K. We are not going to use the decimal value. Use the decimal value and your answer is less correct. We don't like less correct answers. The goal of this unit is to learn to use these numbers that you don't like, even though they are numbers. All right, so here we are in Desmo. So I'm going to do ln 1/2. Oops. 1/2, and I want to say divided by 5,700. So notice I get this negative decimal in there. I have a negative because it is decaying. If it was growing, if it was multiplying, that K would be positive. So that's why I say you don't have to remember that K is negative for decay. It happens naturally here. And then you can see how long this decimal is. That is a really small decimal. And I don't want to type those. I don't even want to write those. This is much easier to write. So that is what we're going to use for K. We are not going to use the decimal approximation. We do not use a decimal approximation. We use the actual number. Okay, so here we are. We're ready to actually answer the question. It says, if a fossil contains 1/5 the carbon-14 contained in a contemporary living sample, estimate its age to the nearest 1,000 years. Okay, so we know what K is, right? So now we're saying, when is it equal to 1/5? So I can do the fraction 1/5. You can change it to a decimal 0.2. It's all going to be the same. 1/5 equals 1 for like 100% of what should be there, even though it's not. So I'm going to not write 1. E. Instead of K, I know what K is. It's ln 1/2 over 5,700. And then T. All right, so we're going to solve this equation. I need to get rid of the E so I can get to that exponent. So I'm going to ln on both sides. That's going to clear the E. So I have ln of 1/5 equals ln of 1/2 divided by 5,700 times T. And I need to solve this for T. So what I'm going to do is I'm going to divide this off. Keep in mind when you divide with a fraction, it's going to flip. So this becomes 5,700 times ln of 1/5 divided by ln of 1/2. And that is t. So we're going to go back to Desmos and we're going to see what number we get. Because it does say round to the nearest 1,000 years. All right, so we're back here at Desmos and let's see what we get. So I have 5,700 times ln of 1/2. So I'm going to put 0.5 this time, just so it's easier with all these parentheses. And I'm going to say divided by, oh, nope, that's not 0.5, that's 1/5. So it should be 0.2. 1/5 is 0.2. So I'm going to say divided by ln, this time is 1/2, so it's 0.5. All right, so this is the approximate age of that fossil. So it looks like 13,230, looks like 5 years. It says round to the nearest 1,000, so it's about 13,000 years old. So that is carbon-14 dating using half-life. This concept of half-life is very, very important. I'm sure Miss Barnes will tell you all about it, how it applies to chemistry. Okay, so we have a more contemporary half-life problem. So it says, in some instances, links posted on Twitter experience a half of their hits H within the first 2.8 hours. So they're telling you essentially the half-life is 2.8 hours. And so we need to solve for the rate. So we need to actually solve for what that K value is so we can write the equation. So we'll start with 1/2. It literally says half of its hits in the first hour, so, or 2.8 hours. So this is the half-life equals E. And we know that it takes 2.8, so that's our time, 2.8. And we need to solve for K. So we're going to clear out E with ln. You're probably noticing a pattern by now. So I have ln of 1/2 equals 2.8 K. So if I solve for K, K is ln of 1/2 divided by 2.8, whatever that number is. So when I write the equation, H of t depends on the initial hits, H sub 0. Anytime you have this little sub 0 in there, that means the initial. That means at time equals 0. I'm not going to worry about K being negative because I solved for it. That is taken care of in the ln of 1/2. So I have ln 1/2 divided by 2.8 t. That is our equation.